Hi everyone! This video is going to deal with subatomic particles, their mass, their charge, and their location. And this is really the heart of reagents chemistry, because once we start understanding the inner workings of these subatomic particles, we can start understanding the elements themselves, which means we can understand how they behave, why they act the way they do, and this is the foundation for all of that knowledge. So we now know of three subatomic particles that exist: the proton, the neutron, and the electron. These subatomic particles each serve their own purpose in the atom. The proton is the positively charged subatomic particle that was the reason for the deflection of the alpha particles in Rutherford's gold foil experiment. The neutron is the neutral particle that exists alongside the proton that helps to make the nucleus such a small, dense sphere that was able to deflect those alpha particles from Rutherford's experiment. And the electron is the negatively charged subatomic particle that J.J. Thomson discovered when he did his experiments with the cathode ray tubes. So what we know about these three particles is that they all have distinct charges. The proton and the electron have a charge that's equal in magnitude but opposite in sign, which is to say, for every proton, if you have one electron to counter it, you're going to come out overall neutral. So each proton brings a +1 charge, each electron brings a -1 charge, and each neutron just kind of carries some mass along with it, but no charge. Speaking of mass, what we know about protons and neutrons is that they compose the majority of the mass of the atom. Remember, the nucleus is this incredibly dense center that's most of the mass of the atom itself. And because we can't talk about atoms, really individual atoms at least, using the unit of grams, the unit that we use when we discuss mass of subatomic particles is AMU, or atomic mass unit. This was a unit that was kind of defined to help us discuss such small masses. And the AMU, whether it's worth discussing or not, is defined as 1/12 the mass of a carbon atom that has an overall mass of 12. So this tells us the element, and this tells us the mass. So we've defined the atomic mass unit to be 1/12 of the mass of an atom with a mass of 12. Does it really tell us a lot about atomic structure? No, but it's something that's at least worth having in your back pocket if you need to talk about what an AMU really is. So both the proton and the neutron contribute 1 to the overall mass of our atom. The electron, on the other hand, is so tiny that it really has no bearing on mass whatsoever. Yes, it does actually have a tiny bit of mass, over like 8,000 times smaller than a proton. But big picture considered, when we're looking at the mass of the atom, it contributes absolutely nothing. And again, what we know from Thomson's experiments and Rutherford's experiments is that the proton and the neutron are both located in the nucleus of the atom. They're what make up that small, dense, positively charged center. The electron, on the other hand, has to be floating around outside of the nucleus. And we'll pinpoint that location down a little bit more specifically later on. With all of this information, what we can really start discussing is some of the characteristics of particular atoms, and the vocabulary that comes along with it, of course. So over here on the right-hand side of the page, I've got the nucleus of an atom drawn out. And I've said I've got 5 positively charged protons and 4 neutral neutrons. So of course this represents the nucleus of the atom, knowing that these two particles together are what have formed it. What I also know from back in the day of Dalton is that overall an atom is always going to be neutral. So if I've got 5 positively charged protons, the only thing that can get this overall charge to become neutral is if I had 5 negatively charged electrons somewhere out here outside of our nucleus. We'll get a little bit more specific about how these 5 electrons are distributed as we learn more about atomic structure. So when I talk about the nuclear versus the net charge of this atom over here, what I know is nuclear has to do with the nucleus. And the nucleus is composed of protons and neutrons. Of those two subatomic particles, only protons carry a charge with them. So in the nucleus, there's only one charged particle, and that's the proton. So if I want to know the nuclear charge, what I really want to know is the total positive charge. And that always is going to come from the number of protons. That stands in contrast to the net charge. Net kind of means overall, right? So over here, when I look at the net charge, what I'm looking at is not just what's going on inside the nucleus, but what's going on in the atom overall. And again, in this case, I've got 5 positively charged protons and 5 negatively charged electrons. If I've got 5 positives and 5 negatives, they kind of cancel one another out in terms of their charge, leaving me with a neutral atom. So the net charge has to do with total positive minus total negative charge. And we know, of course, from our subatomic particles that the total positive stuff is really number of protons, and the total negative stuff is going to come from our number of electrons. And that's exactly how you can always calculate a net charge of any given atom. Now, it'd be pretty boring if you only dealt with atoms, because by definition, an atom is going to be neutral. But if I start taking electrons away or adding them in, maybe altering this number from 5 maybe down to 2, what I see now is that my number of protons and number of electrons are no longer the same. I've got more positive protons in the nucleus than I do negatively charged electrons outside the nucleus. So 5 minus 2 gives me a net charge of plus 3. So when your net charge is not equal to 0, the term we have for that is ion, and we'll talk lots about ions as we move through the year, but just know that that term is always going to refer to some atom that's had its number of electrons changed in some way. Last but not least is this idea of how mass plays into things. When we talk about an individual atom, we can talk about how much it weighs in atomic mass units, and we call that mass its mass number. So this is how much a single atom weighs. And we know that all that mass is going to come from our protons and our neutrons. And this is in one single atom. So when I talk about mass number, what I'm really referring to is those subatomic particles that contribute the mass, how many of them there are in total. And if we look forward when we start talking about isotopes and changing the mass number, that's where we're going to start talking about more complex notation. So be sure to watch the video on isotopes to further your understanding of mass number and what it means about the structure of the atom.